Okay, welcome to A/B Testing Myths. I'm Ronny Kohavi, and this is going to be an interesting talk for you. I'll just say a couple of things. If you have something that's unclear about the slide, you can unmute yourself and ask a question. If it's sort of not directly related, I prefer that you put it in the chat. I will answer many of the chat questions. But if you have a question that maybe will be discussed at the end, then use this link, the Myth Suggestions link, which I put uh, in the chat, and I'll put it again. Um, and then vote, and maybe I'll take a couple, but I will answer anything that's got more than a couple of votes in writing offline, so you'll get an answer to everything that you want. Uh, I estimated about 100 people will join, and we are at 99. So, wow, pretty good estimate. Okay. What are we going to do today? I'll do a quick intro, and we're going to talk about four myths. And then, depending on time, we'll look at the top voted questions from this. And I did not put the correct link in the chat. Let me just put the correct link. There we go. This is the link for you to vote on some of the myths out there. Okay, so first of all, who am I? Why should you listen to me? What are my biases? PhD in machine learning from Stanford, director of data mining and personalization at Amazon. One of my teams that I was when I was there was WebLab, the experimentation system. This is where I had this epiphany that, boy, we do not know what we're doing, and most experiments fail to move the needle. I then went to Microsoft and formed the experimentation platform team, which went through rounds. I then led it at Bing, and then out of Bing into all of Microsoft. Was a technical fellow and corporate VP. And I want to show you the scale that we ran there. Every workday, we were launching more than 100 new treatments, right? So pretty reasonable, high scale, lots of data across 15 product teams. Um, then I went to Airbnb, led the relevance, personalization, and experimentation. And I think many of you might have heard about this book, sometimes colloquially called the HIPPO book, because most people know the HIPPO stands for the highest per person opinion. It's a term that Avinash Kaushik and I popularized back in 2007. If you're interested in the history, there is a link there. And somebody asked in the chat if these slides will be available. And the answer is yes. You will get an email with the link to the recording and the link to the slides. Okay. I think most of you know what experiments are, but let me just get the terminology right. It's a trivial concept. You got users coming in, we split them into two or more groups. I'm going to usually talk about A, B as if it's only two, but I highly recommend that you do more than two. One is the control, or the A, that's typically your existing system. The other one is the treatment. This is some new thing that you are trying, you're introducing some new feature, and then you analyze, right? You instrument as much as you can about what the users are doing, their behavior, and your own system, performance, calls, failures. Um, so A/B test, simplest controlled experiment. ABN is sometimes used, although these days most people refer to AB even if they're running ABN. The idea is to compare more than two variants, so A, B, C, D, not just two. And again, as I said, highly recommend that you go for more than two. I think the sweet spot's about three or four. After that, you start to get fragmentation and you lose statistical power, which we'll talk about briefly. Lots of equivalent names have been invented for this. Microsoft used to call these, still calls these flights. Um, Google sometimes calls these 1% tests, and YouTube, another group, is a terrible name because nobody runs at 1%. Most people scale to higher percentages like 50-50 or a third, a third, a third. Bucket tests, good name. That's the way you bucket users. Field experiments used a lot in research, typically in medicine. Facebook and Meta use that. Randomized clinical trials is, if you're after the pandemic, you're familiar with that name. Again, very common in medicine. They're all equivalent. They're all based on, R.A. Fisher's books from the 1920s uh, that established the field. Now, you must run statistical tests, right? You're sending users to the control, you're sending users to the treatment, you're logging metrics, and at the end, you have to say, I'm going to run a statistical test to see if the difference, and there'll always be a difference between these groups, if this is due to chance, right? And so this is the best scientific way to prove causality, right? That is the key word here. We're trying to claim that the changes we introduced in the treatment caused the metrics to move. Okay? Very, very important. We're trying to claim that the changes that we made caused the metrics to move. They're not just randomly different due to chance. We have caused them to move positively or negatively. And then, we call a result that meets certain conditions a low p-value. We call it statistically significant. But very important to understand, we're trying to get causality here. Most of the data mining business efforts that people do, machine learning models, establish correlations. We are able to establish causality. I'll answer quick questions. The treatment group always 50? No. If you're running a three-way, it's a third, a third, a third. If you're running a four-way, it's a quarter, a quarter, a quarter, a quarter. And sometimes you run with less, especially in the beginning of an experiment to avoid risk, but that's ramp up covered in other places, not here. Okay, so myths. First of all, I love this quote called Cunningham Law. Best way to get the right answer on the internet is to ask a question. Is not to ask a question, but to post the wrong answer. So I've seen this a lot. People say something, it's, I don't want to call it by names. It's clearly incorrect. And then people start discussing it, and there's some evolution of what's going on. I'll share with you one example of that in this presentation of a claim that was made about how much better it is to have rounded corners than square corners. The myths are not true in general, but they could be true in limited scenarios. And this is what I want you to understand. Very important. For example, there's a Slido submission. One of the questions that was made for this meeting as a myth, the person wrote, changing an image or headline is a valid test and you will reach statistical significance, right? So he put that as a myth to discuss. First of all, I want to say reach is a bad term. In classical statistics, if you're running classical A/B test, there's no notion of reach. You're supposed to determine the duration of the experiment in advance and test at the end, right? Otherwise, you're peaking and it's invalid. But assuming that this is done maybe using sequential testing or more advanced, or that the user really didn't mean reach, he said just you will achieve statistical significance at the end. It is true that in most scenarios, you will have a tiny effect. And you will not be able to detect a small effect unless you're very, very large. But I worked at Microsoft and we had lots of data, and I did see wins from tiny changes, sometimes to images or headlines or to copy. Okay, so the myth has to be contextual. If you are a small company and you have hundreds of thousands of users, you're not going to be able to detect smaller changes. If you're a large company with tens of millions of users, you might be able to do that. We have examples where we changed font colors and saw a win. We have examples where we changed something, small around the shape of an object or an image and saw a win. So what I'm going to talk to you today are myths, and I'll say try to convey to you when they are, in general, they're going to be false, like doesn't apply to everybody, but there may be conditions under which there is a grain of truth to it. Okay. Okay, so I'm going to start with a concept that is extremely important that a lot of people don't understand or are not aware of it. Actually, I'll answer one more question. Vineet says, my previous company used to run 80% treatment, 20% control. Is that a good way? No, that's a poor way. There is a post that I did just a few days ago, so you can go to my LinkedIn, about why you should be running a uniform distribution. This same percent applied to control and treatment. There are like 4 good reasons why you should do that. There are certain cases where you can run uneven splits, but you have to be super careful. You lose a lot of trust. Okay, cool. Got the response here. So power. Love this statement by Jacob Cohen, wrote this really famous book in the 1990s, is when I finally stumbled onto power analysis, it was as if I had died and gone to heaven. So I think most of us don't think of power as extremely as Jacob Cohen, but it is a very important concept that, if you've not heard about it, or you're not sure what this is, it's really important. What it says is this is the probability of detecting a difference between the variants when there really is one, right? So you're running two variants, an A and a B, and the statistical power of your test is the probability that if there is a difference, say B is better by 5%, that you will detect it. Okay, so in order for power to work, you have to give a number, the MDE, okay, or the minimum detectable effect. And so you're going to say, I want to run this experiment and I want to be able to detect changes that are at least 5%. Okay. And I want to be able, now everything is probabilistic in A/B testing, and I want to be able to detect that with at least 80% probability. Okay. So you're running an A/B test. Before you run it, you're going to say, I need 5%. I want to be able to detect a 5% delta. The power formula, which I'll walk you through in a minute as an example, will tell you you need 100,000 users. When you run the experiment with 100,000 users per variant, if the change you made, that treatment, has more than a 5% effect, there will be 80% probability that you will detect it and will be able to call statistical significant. If it's smaller, say it's only 2%, then you are not going to detect it most of the time. Now, you may detect it, and there's going to be the winner's curse. We'll talk about that. But that's the notion of power. Very, very important. Let's look at an example. You're running a website and you're selling some widgets, right? Your conversion rate from a visitor to a purchase during the duration of the experiment, say 2 weeks, is 5%, right? That's your conversion rate. That's how people convert from a user that's entering the experiment to a user that's purchasing in the experiment. And you say, I want to be able to detect a 5% relative difference. This is relative, so it's 5% times 5%, absolutely. Or I want to be able to detect a 0.25 change to conversion from this test. And you're going to use industry standards type 1 and type 2 error, which is 5% is the common type 1 error, meaning if there is no difference, 5% of the time you will call a difference by incorrectly, a false positive. And then type 2, 20%, or what we call 80% power. These are synonymous. So I have the power to detect a 5% delta with 80%. You plug that into the power formula. There are websites out there that give you the power formula. It's a very simple formula. I have Excel spreadsheets out there on the web. The formula tells you need 121,000 users per variant. Okay, so a lot of people are surprised. Wow, that's a big number. And that's one of the lessons that I want to share with you. If you're running an experiment with low power, you have to tell me which of these assumptions you are going to change. Maybe you have a high conversion rate. Maybe you're willing to tolerate larger error. Otherwise, you need a lot of users for a reliable, trustworthy A/B test. Okay. Now, if you're running an experiment with low power, you don't have 80%, you have 50, 20, 10, and you do get a statistically significant result, then you will suffer from something called the winner's curse, right? Provably, this is a beautiful curve that Carlin and Gelman did in a paper. There's the link to it. It shows you how much your result will be exaggerated in expectation, right? Everything is random when you're running experiments with low power. So let's look at this example. If you're running with 10% power and you get a statistically significant result, your effect that came out of the A/B test is going to be exaggerated in expectation by 4 times. So if you have an 8% improvement, it's likely to really be 2%. You just underpowered and the results are exaggerated. If you're running near 5% power, I'll show you examples. Your exaggeration factor is going to be about 25 times. So if you get 25%, you're telling your finance people we just got 25%, it's likely to be 1%. Okay. Um, Let me answer a couple of questions. Is there a problem in having more users than necessary? Absolutely not. Overpowering, I actually highly recommend it. The problem is that you run the experiment longer, right? You could get the result in a week. You're running it for 2 weeks. Um, why is it a good thing to overpower? Your confidence intervals will shrink. You will be more sure of the result, and you'll be able to segment the data more, right? So think about this. You're running an experiment. You have enough power to determine conversion rate, but if you overpower it for conversion rate, you may be able to have a more trustworthy result in analyzing some segment, new users, tenured users, people that came to you from some site, some segment of your users that is interesting. Question: user is a unique visitor, unique visit event. Typically experiments are run by. Um, sorry, I just had a pop up. Typically experiments are run by users. You can run under different randomization units, so you can randomize per visit. You can randomize per page, but there are issues with that. I will say 90% of the time, think about user as your randomization user unit, which is important. Is it possible to see a result that is statistically significant and neutral? Well, again, the word neutral is kind of fuzzy. I'm assuming normally neutral means not statistically significant, right? We call it flat or neutral. So depending on your definitions, I think the answer is no. These are opposite terms. How is statistical power different from confidence? They're related. The more power you have, the more the confidence interval will shrink. Okay, so if your MD is 5%, that effectively means that your confidence interval will allow you to see things that are plus or minus 5%. So if something moves away from zero at more than 5%, you will be able to declare it statistically significant. Yeah, false positive, false negative. Somebody commented, what does 4 times more mean? Is it 4 times the MD? No, this is 4 times the result that you achieved. So if the estimate from the experiment tells you you got a treatment effect of 10%, it's likely to be 4 times smaller, or 2.5%. Should experiment wait till they reach power? No, so power is a pre-experiment concept. You're supposed to run the power formula before you start the experiment and then run the experiment until that number. Because there's no notion of reaching power. It's reaching the number of users that you have enough power. And then you're supposed to analyze it. You're not supposed to peak in the middle unless you do sophisticated A/B tests like sequential testing or a group. There are posts about that if you want. Is it valid to run post hoc power? No, I will give you a link to that. Again, everything depends on the condition. Non-inferiority test, somebody mentions, yeah, so that's a test where you're not looking for, is there a positive or negative effect, but is it not hurting me? So you might say, is it not worse than minus 2%? Does it make sense to do two-tailed? Yes, all your tests should be two-tails, hotly debated in the community. There are posts on that. Okay, I will go on because I want to get through the concepts and we don't have a lot of time. Let me start with the myths. So first of all is number one myth. I did X and I improved revenue by some large number. Okay, here's an example. On Guess the Test, fun website, sends you every couple of weeks an A/B test so you can try to guess it. Here's one example that it was shared on this website, and it had 80 users in each variant. And the claim was, wow, this improves the treatment by 337%, right? Think about large. This is like obscenely large. We're not talking about you're improved by large 10%, which is huge. This is 337. So I ran the power calculation. If I look for an effect of 10%, which is very, very extreme, normally I recommend nothing above 5%. This thing had basically 5% power. At 5% power, the exaggeration is undefined. It's infinite. This means that the experiment just has meaningless. The number that you get could be off by an infinite factor. Right? You can look at this paper for details if you want to read this. There are links to Excel spreadsheets with the formula that you can use. But my key message Do not trust experiments with low power. Next example. This is the real one. This is, remember I mentioned Cunningham's law, Cunningham's law. So it's a journal paper that published last year, and it claimed that rounded corners on buttons on images are better than square. Okay, so this is one example from the paper. If you look at the top, this image of the woman, this button, they're squared, right? They got the square corners. If you look at the bottom, these are rounded, the buttons are rounded. Okay, so they published a series of experiments. I'll focus on the only A/B test that is valid in that paper, right? The others look at eye tracking and other stuff that has lower trust and confidence. But they claim that based on 450 visits per variant, right? So now they're randomizing visits, not users. There was a 55% lift to clicks. And my answer is, wow, this is huge, right? I have never seen a result like this in my life. Tens of thousands of experiments for a metric, like not a fake metric, for something important where you're not just, doing something random. You never get lifts like that. Anything above 5%, I usually call Twyman's law because it's very, very unlikely. Make sure to double check. It can happen. It's extremely rare, but 55%, ouch. So, what was their power? Again, 5%. 5% is infinite exaggeration. There is no meaning to this result. Okay, so we ran a replication experiment. We said, okay, we made a call to the community. We said, who's willing to run this with us? And there's a site that was willing to run it with us, two sub-sites in Norway, and we had 80% power. And the power was the ability to detect at 2%. Notice we didn't try to detect at 20% or 30%. We tried to power it up enough users to be able to say if this moves the needle by 2%. Okay. Now, how many users did we have? 1 million users in each variant in each of the two experiments. Okay, so much larger, 2,000 times larger than the experiment reported in this paper. And what was our result? Not even stat sig. So we were below 2%. We can't say how much it was. It was consistent with 0, right? The effect that we got, the estimate 0.56 rather than 55%, right? So it's 100 times smaller, but it is still consistent with 0. So even with 1 million users, we can't say that this number is correct. It was not statistical, or this number is sort of not statistically significant. It wasn't. So could be 0. There was a confidence interval around 0.56%. Great example. Okay, Chloe says can't even consider. So the author had reasons why they think this is true, gave all the psychology research about how people prefer rounded objects and all that. ASR asks, power analysis behavioral and sequential. Yes. Okay. Message, do not trust experiment with low power. Second myth, 5,000 users are enough. Okay, so I'm not saying 80 or 100 or 500. I'm saying when you see an experiment with 5,000 users, under reasonable assumptions, which I'll state in a minute, it's a myth. Okay, so what are my assumptions? I mentioned them before. Conversion rate of 5%. If you have a lower conversion rate, you're going to need more users. MDE, the ability to detect the change of 5%. Again, if you want to detect something smaller, like a 2%, you're going to need more users. I recommend, there's a link here to a post, that in online settings, you never pick an MDE over 5%. That should be an upper bound. If you have enough users, go for 2%, go for 1%. But don't pick 20% because that just never happens. It is so super rare. Most likely, you will get meaningless results with high exaggeration factors. And then industry standards, 5%, 80% for type 1 error and power. And you get this number. So 121,000 users per variant. So you need like 200,000 users to run an A/B test in classical A/B settings. Now, what are exceptions, right? I want to make sure that you understand it. So first of all, you could go for a large MDE. You could say, I'm looking for a huge change. For example, you're building a vaccine for COVID. You're going to look for a large effect. You're not looking for a 5%. You're looking for 50%. right? If you plug in instead of this 5% an MD of 50%, you only need 1,216 users per variant. This is why if you look at the COVID tests, they ran them on some, 3 to 4,000 users. Because they're not looking for some 5% improvement. They're looking for this vaccine better be over 50% effective. And the power formula has this term in squared. So I've increased MD by a factor of 10. That means I need 100 times fewer users. Okay. Boris asks effectively the next bullet point, which is high conversion rate. So if instead of checkout, which is normally 1 to 5%, you're going to look at some clicks or some upper funnel metric, then yes, then you will need fewer users. So if you're able to change this number to 20%, then you will need fewer users. My point is plug it into the power formula, make sure you power it enough so that you can trust the results. And if you see out there some website that tells you, oh, I ran this amazing thing, and you look at the number of users and it's 5,000, don't trust it. Okay, myth 3. Actually, let me answer another question in the chat. Most websites do not have 120K per variant. What do you recommend? So, yes, if you don't have enough users, figure out which assumption you want to violate, or go trust industry standard recommendations. Look at sites like Good UI. Good UI, Jacob Lanowski has a bunch of patterns and results from sites that say whether this worked or not and all the statistics. So you might have to rely on conventions, copy Amazon. They run everything. I was there. Everything is A/B tested. So if they use a pattern, you might start off by saying, I'll copy the pattern until I grow and have enough users for A/B testing. Emery asks if we run email experiment for CTR, that's usually about 1%. Does that mean we need even more users? Absolutely. So remember this statement. If you have a lower number, you're going to need more users. The power formula will give you a bigger sample size that you need. Okay, myth number 3. You can do pre-post if you don't have enough users. So really nice talk by Elena on 10 growth tactics in Lenny's podcast earlier this year. I liked it. But she makes this one recommendation, and there's a link here if you want to hear that. I'll show you the snippets from the video. She says, you can do pre-post if you don't have enough users to run an A/B test. Okay, so I want you to listen to what she's saying, and I'll play the video.
My rule of thumb, if we cannot collect the sample size in a month, we shouldn't test it, period. Because it's just then it's not fast enough. We should just go and do pre versus post. Pre versus post is pretty powerful.
Okay, so pre versus post is very powerful. If you don't have enough data, maybe you should use that. This is a myth. Okay, when you run A/B tests or online randomized controlled experiments, they are the gold standard. And one reason for them to be that they are the gold standard is sensitivity. They are the most sensitive procedure that we know. So you cannot tell me in general, right? There are certain scenarios where you can do models, but in general, if you make few assumptions like the ones you can do an A/B test, nothing's going to beat it. Not regression discontinuity designs, not pre-post. None of these things are going to work better. We're running the control and treatment together, and therefore that takes care of a lot of the variability in the data, and no other method comes close to A/B tests in the amount of sensitivity. Okay. Somebody asked if she's talking about difference and differences. No, pre-post means you look at the data before, you look at the data after, and you look at the difference. Right? It's not even diff and diff. It's even more primitive than that. Yes, Riley, what does pre-post mean? It means you look at the conversion rate at the beginning, you run it for 2 weeks, you look at it at the end, and you say, did it go up or down? So very unreliable. It's true that if you don't have enough power, you can't run trustworthy A/B tests, but you surely can't detect anything with pre-post, right? This is, to me, that's like saying, oh, it takes too long to fly from New York to San Francisco, so let's drive. Right? That's clearly going to make it worse. Okay. Myth number four. Running concurrent experiments is invalid because of interactions, right? So the combined effect is not equal to the sum of the individual effects. So let me give you an example here. Experiment run one runs a treatment that improves by 0.5. Experiment two runs a treatment that improves by 0.6. If users are exposed to both of these, right, they fall into both the treatment in experiment one and the treatment in experiment two, then we expect them to improve by 1.1 by this sum. If they don't, we have an interaction. Okay, if it's larger than 1.1, which again could be, it's called a synergistic interaction. If it's smaller, it's called an antagonistic interaction. So let me give you an example. I know it's extreme, but unrealistic, but it makes the point. You've got a team that is looking at different font colors. Again, not an experiment I would recommend for any small site unless you're massive. At Bing and Google, we ran those experiments and we were able to optimize font colors and get a huge win. But most sites not recommend to run this experiment. This is for the example. You got experiment two, which is trying different background colors. Okay, now some users are going to fall into red on red, right? So here's one. We're trying the black versus red. Here is another experiment. We're changing the background from gray to red. The users that fall into the treatment see red on red. Boy, do they have an interaction, right? They can't read anything. So that's an extreme example of an interaction. Okay, so why am I calling this a myth? Because people are afraid of interactions, but there are simple ways to deal with them, right? And they split into prevention and avoidance. Okay, so the first one, and there's a link to the paper here. Somebody asked if I'm in the chat if we'll give the slides. Absolutely. You'll get an email with a recording in the slides. So we said prevention. Have the system try to detect the use of the same resource. We had this at Microsoft where you're running an experiment. You could name resources that you were using. And then we warned you that, hey, you and some other experiment are changing some resource. You may be interacting. Watch out. Right. So that's prevention, raising awareness that this could happen. Be careful. If you're concerned, run them sequentially, run them one after the other. But there's more than that. We can't expect that everything will be caught using prevention. So we do a detection check. Every day, we do a test and we say, look, is the treatment effect of two experiments additive, right? Or is it different, right? This is a classical A/B test, right? You assume that they're equal, and if they're not, you say, hey, there could be an interaction here. And you can do this, and you do have to do this for all pairs of experiments. So this is an expensive run, but it is possible. We did this. But I want to say what happened and why am I not concerned about it? It was super rare. We were very concerned about interaction. We discovered they don't happen. Okay, at Bing, where we were running 1,000, 2,000 concurrent tests. And remember, these are all running on effectively one page, right? The search engine results page, right? Bing, you type a query, you get a result. On that page, there's 1,000 concurrent experiments running. We found a single interaction maybe once every 1 to 2 weeks. Right? And typically it would be some bug, not even a fundamental interaction. Okay. So interactions to a small degree is not even detectable. It doesn't have a lot of impact on your results because most experiments have small effects. So that you can't even interact if the other experiment doesn't have a strong effect. Because remember, you have to have the sum not be additive. Um, and so there are references here you can read. We wrote about it in the summit, which a lot of very famous companies attended to give their opinion. Everybody agreed this is not important. Lucas Vermeer, who was at Booking, now at Vista, has a very nice blog on this. Statsig blogged on it. Microsoft blogged on it. We wrote about it in our book. It is something to be aware of, but you will not be able to scale unless you run concurrent experiments. And we had no problem scaling to thousands of concurrent experiments. Question in the chat, is that because your volume was so high? No, I mean, high volume allows you to look for smaller effects, so we may be able to detect interactions more than you might, but I've worked at smaller volumes and you can scale. Okay, let me do a pause here. If you want to learn more about A/B testing, um, I teach 2 online courses on Maven. First one's called Accelerating Innovation with A/B Testing, 5 sessions, 2 hours each. Class starts in about 10 days on March 3rd. Uh, there's a link here that you can use, and the first 5 people to use it will get $250 off the course. Let me just put that in the chat for anybody that wants to look at it. And then if you are an expert and you took the first class or you have equivalent knowledge, which I will say is not common, uh, then you can take my advanced class. It is new. We just did 1 cohort recently after a physical meeting, and it is 2 sessions, sorry, 3 sessions. We extended it to of 2 hours each on these 3 days in the middle of March, so in about 4 weeks away. And there is your discount code for the first 5 people to use it. So I've got a few more minutes, and I will be happy to stay a little longer if people need. I will go through the Slido now and take the highest voted questions. Actually, let me just make sure to give you the link in the chat. Suggestions. Oh, somebody beat me. No, that's not it. There we go. There is the link to the Slido. So the first ones are the ones that I talked about, and I'm going to take the questions from the top voted. Is Bayesian better than frequentist? This is a question that statisticians have been talking about for tens of years. I have a post on it. I discussed this in my lightning lesson in the past. So if you go to Slido, there's a link there to the recording and the slides. In 30 seconds, they're answering different questions. And if you make them answer the same question, they typically will give you the same result. But they make there's one key difference. In a frequentist setting, which is usually what I see people use when they implement an A/B testing platform, you say, I'm going to run the experiment, and if there is no difference between the treatment and control, something called the null hypothesis is true, then I will make an error 5% of the time at the most. Right? It gives you this guarantee that you will not make a large error in terms of getting a statistically significant result. Bayesian flips it around. Bayesian says, if you have a prior and you know something about the probabilities, I will tell you how to go from that prior to a posterior probability. That stage of transferring from prior to posterior is provably correct under the common assumptions of Bayesian. But the result you get depends on whether your prior was correct. So if your prior is wrong, all bets are off. That's why we don't like it, because, well, how do we know to trust the prior? Right? Most ideas fail, and therefore I don't think a reliable prior can be set, again, in most settings. So in order to avoid that, people use what are called non-informative priors, and then they get back to a result that typically is the same as A/B testing. Lots of debates on it, lots of posts. If you just ask me, I'd go with this classical frequentist approach, and this is what most systems out there that do A/B testing have implemented. Okay, next. Again, I'll give, there's links in here, and you can read more from the links that I'll provide. I'll answer anything voted more than twice in writing after this meeting. So Sebastian says, well-executed A/B test guarantees results will generalize to the entire production environment. There are no guarantees, right? So look, everything is probabilistic, but the term that is needed here is called external generalizability. Can I generalize from the result that I got in an A/B test to the future. And that depends on seasonality. Maybe I ran this test over a holiday, less reliable. Maybe I ran this test for too short a period. That's why we recommend you run for at least a week or a multiple of a week. These are things that help external generalizability, right? But there are no guarantees. What we have done in many cases is do a replication run. You run an experiment, it usually fails, but when it succeeds, you can do a replication run and say, okay, let me try that again. And if it replicates again, then a lot of the concerns go away. And we have seen that most of our, trustworthy results do tend to impact the metrics they were designed, and there is growth over time. So it is a myth. There is no guarantee, but it's close to high probability as you can get. Next one, I wrote that and it was voted high. So the A/B test was not statistically significant. So the treatment effect is zero. That is a myth. If you get a non-statistically significant result, it means that you can't claim with high probability that there was a big effect, but the effect could be small. So depending on your confidence interval, if you're running with an MD of 5% and the reality is 4%, you will get, with high probability, a not statistically significant result, but it is not zero. Right? So you can't claim zero, but you can claim it's small enough. And if you take your MDE to be something that's important for the business, I want to be able to detect changes above 2%, then that's basically it. When you run an experiment and it's not statistically significant, you can say it's not going to be very material to the business. Because if it were, it would be above 2%. And then we would have a high probability of detecting it. I talk about this in my class about how the US allows right turn on red for those of you that drive in the US or have driven in the US. And that was based on a faulty experiment where the result showed not statistically significant difference in accidents and injuries, but they had so little power that later test shows that, boy, that we are, right turn on red increases deaths of pedestrians and bicyclists by massive numbers. Okay. You don't have to reach at least 80% statistical significance to declare a winner. You don't have to use 80% power. By the way, this term is strange. They say, whoever asked this question, 80% statistical significance. I assume they mean 80% power. You can use with lower power, the probability of detecting a true result comes down, and then there's this exaggeration problem. Okay, the flip of this question is, do you use a threshold of 0.05 on your results for p-value? That's called the alpha term. And again, if you use a higher alpha, your false positive rate will go up. There's a term called false positive risk, which is the actual probability of making an error, right? And it's different from what people interpret the p-value to be. So if you're running with 0.05, the probability that you're making an error might be 20%. And that depends on this prior that you have or your pre-experiment probability of the null being true or false. Next question, can the same control group be used to compare more than one treatment group for different metrics? Yes. Yes, so you can run a single control group and then have different treatments. And it's an ABC test or an ABCD test, right? So very common. In fact, I do recommend that you do that because our success rate is so low. It's worth it. You're implementing some new feature. Why don't you implement two variants of that feature? And maybe you'll be surprised that the C version wins. So absolutely. There is for the advanced people, it becomes more sophisticated, harder to do when you do triggering, but still possible to do, still very, very useful. Let's see. Results from different site tests should not loosen your requirements for the same test on a similar site. Well, I assume the myth should have been phrased in reverse, but I think this is partially true. What do I mean by that? Is if you see results out there that publish that, let's take a result that I think is almost uniform, that performance improves key metric, right? If you're able to make your site faster, you will improve conversion rate and revenue and other things. Um, I've seen this replicated so many times. I think the default should be yes, if you're able to improve it, performance, you will improve your business. Now, the degree to which you get an improvement, you will have to run your own A/B test in order to be able to prove that. So there's a talk out there. There's a whole chapter of this in my book, chapter 5, on performance, and we show how to run this experiment. It's not easy to run a controlled experiment because you don't know how to speed up your site. But under simple approximation, like linear approximation, Taylor, first order Taylor series, you can run the opposite, which is a slow down experiment, and then see what this does and say, boy, if I were able to improve this, this is what my benefit would be. To give you a fun statistics, at Bing, if you were an engineer that was able to improve the performance of the Bing server side, right, the time to generate a result by 4 milliseconds, right, 4/1000th of a second, you just funded an engineer for a year. Okay, so small improvements to performance were worth a lot of money. 4 millisecond funds an engineer, a whole head count with all the Microsoft overhead. Okay. Maybe to summarize this question, there are sites out there, Good UI, what's the I guess the test that I mentioned before. They have results that people have run, and if you see a pattern, then absolutely you can say I'm putting a higher probability that this will work because it has replicated X time. Um, Let me actually give you a link for a project that we are doing called Trustworthy A/B Patterns. We've identified 5 patterns that are interesting, and we're calling for replications out there. One of them was the one I shared with you, the square versus rounded corners. If you want to join this project, we will consult for free. 3 of us, myself, Lucas Vermeer, and Jacob Lanowski, we will help you run a trustworthy A/B test as long as we're allowed to publish the result. Okay. Gigi says, how should we present an A/B test result? Is the threshold 5% that rigorous? For example, yeah, so I covered this. To get a trustworthy result, you need to not just use a 5% threshold on your p-value, you have to have enough statistical power. That is a very common mistake. Low power experiment, do not trust it. Eva says, in order to estimate the overall impact of a set of experiments on a chosen message, we can just sum up the individuals. Ah, beautiful question. Um, it is a myth. I'll just state, as phrased, it is a myth. You can't just sum up and say, I've run X experiments, I'll add them up, and this is my overall impact. Why? Because one, there's a certain probability that you have a false positive. You should take that into account. And two, even at 80% power, your result will be exaggerated. Now, it's not going to be exaggerated by a factor of 2, but it will, on average, be exaggerated by 13%. So when you got that 1.5% improvement, you should really multiply by 0.87 to get a more unbiased result. But that said, don't overcorrect. We have been able to show at Bing and in other places that when we have successful experiments, it shows up at the end of the quarter or at the end of the year, again, with a haircut. So as a rule of thumb, and there's posts on it that I did that you can post, and I'll give you links in the Slido. We recommend applying a haircut of something around 20%. If you're in a multi-sided marketplace, maybe go 30%, but you can add up, apply this. There's also a recent Netflix paper. They do a whole Bayesian model, more sophisticated, to estimate the overall impact of their experiments at Netflix. Really another way that you can do. I will end at this point. I want to thank everybody for a session. Lots of interactions, good questions. You'll get a link to the recording. You'll get a link to the slides. You can look at the Slido later. I will answer all these questions that were voted with more than 2 votes in writing so you can have them. Thanks, everyone. Have a great day.
Hey, Dr. Ronnie.